Hello everyone. The experiment that we will be demonstrating today is to find out the focal length of a convex lens. Generally, till class 10, what you have been taught is to find out the focal length using a screen and the image of a distant object. That's how we were finding the focal length. But now we have to increase the accuracy of our experiment, and that is done with the help of these two needles which you can see on the optical bench. Now let's understand the setup first. This is called the optical bench. It has a 1 meter scale starting from 0. Let me show you. Yes, you can see 0 here to my left and 100 on the right side. Right, I hope it's visible. Right, so these are called the uprights. We are using 3 of them here. One of the upright has the needle which is serving as the object, the other one is serving as the image, and this upright is holding the lens. Now you can see it's a convex lens, thick in the center and thin at the edges. Now the step 1 is to find out the rough focal length of this convex lens. Now before that you have to also understand the least count of the scale that we are using. Now here you can see that the scale has 0 to 10 mm it's written, and in between when you find out the least count, it's 0 here and then 1 centimeter. So the least count will be 1 centimeter divided by the number of divisions, that is 0.1 centimeter or 1 mm. So starting with the procedure to find out the rough focal length. Keep on noting down everything on the sheet. Okay, now for the rough focal length. To find the rough focal length, just focus on a distant object and get an idea about the focal length. We will improve the accuracy later. So this is how you place it, and on the other side of the screen you see a real image forming. It has to be a sharp image. Yes, I think it's pretty clear. You can able to focus the leaves and you're able to see the image, inverted image of the windowsill as well as the leaves. I will note down the value of the rough focal length. Now mirror we are keeping intentionally at 50. The lens upright. Now please notice that there is a scratch mark. This is the scratch mark on the upright. It is coinciding with 50 of the scale. Okay, so that's the location of the lens holder, that is upright and at 50, and this focal length comes out to be, you can see the upright here and the scratch mark. This is the scratch mark here. Let me just take it closer. And it's 60.2, right? 60 and 2 divisions after that, so 60.2. So the focal length here will be 60.2 minus 50, 10.2 centimeter. So that's the rough focal length. Now we will start the experiment. How? We have to refine our result. So we will keep the object at 2f, twice the focal length, and keep the other upright towards our side and move the upright back and forth, okay, forward backward, and then get a clear image through the lens. So just observe how it is to be done. Adjust the level, because what we are looking at is the image of the same size and inverted through the lens. So why are we moving it forward backward? We have to remove the parallax. Parallax, I'll just show you what it means. The inverted image of the object and the image needle which is representing the image should be of the same size and without any parallax. Now see here, let me try. Now it's visible. You can see that I am moving the lens of the camera forward backward. You just see a very slight parallax on the right side, very little. That can be adjusted. Yes, it can be adjusted with the help of fine tuning. Now either when initially you should move this upright forward backward, okay, and then when there is a very little parallax left, use this fine tuning needle to move it so that the image as well as the image is what you see as the inverted one, and object is the one which is behind, and image is being represented by this upright. Object is being represented by the upright behind. So now the reading that we have, this is the location of the image 30.6, and here is the location of the object at 70. Right? So this is what we have noted down. Now what we are going to do is move this object needle away by 2 centimeter. Okay? Only by 2 centimeter, and move the needle forward and move the image needle forward to locate the image. See, the lens forms a real and inverted image. We need to locate it with the help of our image needle. Now when we move this, since we are moving the object away from the lens, so we have to move the image needle closer to the lens, and please move it very, very slowly and ensure to remove the parallax. Once again, you can see that now the image is slightly magnified because we have moved the object behind, and the image moves closer and the parallax is removed. Okay, like this we will take 3 readings. Okay, now once more we move the object 2 centimeter away from the lens. And locate the image by the same procedure. See, once you have removed the parallax, then it doesn't take very long to remove it for subsequent readings. Right? You can see the location of the image once again. Now these are the locations that we have of the image. Okay, one more reading by moving the object further to 76 and repeating the procedure. Okay, now finally, this is the set of observation table that we have. The first 4 readings you can see we have just taken on the setup, but the remaining 3 readings we just get by interchanging the object and image distance. That's alright. This is how it is done. And as a result, we have 7 points now. The first one is when the object is kept at 2f and the image is also formed at 2f. So you can see that the result is pretty close, 20 and 19.4. So there is just a small error of 0.6. Next, we move the object needle by 2 cm away from the lens, again 2 cm, again 2 cm. So that makes it 3 other readings that we have taken and we've located the image. Then after that, we have interchanged these values. As a result, now we have 7 observations with us, 33, 72 and the values 17 and 22. Okay, now next step is to plot the graph. When you plot the graph has to be plotted in the second quadrant. Why in the second quadrant? Because the object distance is always negative. So you have to take it on the negative x-axis and image distance on the positive y-axis, because the image is formed on the other side, that is the right side of the lens. Choose the scale carefully. 2 cm for 1 cm of graph is advisable, works well. So first you label what we are plotting on x and y axis, then write down the values, scale. Scale has to be written on the graph. Without writing the scale, the graph has no meaning. You see 1 centimeter x-axis, 2 cm equal to 2 centimeter of our measurements or reading. Similarly, 1 centimeter y-axis is equal to 2 centimeter of our observation. So with these readings, we will plot the graph. Now in the table you can see that we have found out the object distance and the image distance here. Object and image both have to be negative. We've not mentioned negative sign over here, but because the object distance is negative, you have to be marking it negative here. Minus 20, minus 22, minus 24, or you can put it on the top here. Okay, now calculating the object distance, it is 70 minus 50. See here. And for the image distance, 50 minus 30.6, so 19.4. Like that you calculate all these. Now the graph is plotted. In case there is any point which is not lying very well on the graph, it can be missed, it's okay, it's alright. Now the point where both the object and image distance are equal, that is the point which gives you the focal length. So you measure that distance. Alright, now see the graph carefully. This is the graph that has been plotted at 20 and here 19.4 because the least count is 0.2 for each division. So 19.4 and 20, the focal length, or it's coinciding. Here it's making a equilateral kind of a triangle, here a square. Okay, so sort of, not exactly. So this is the point which gives me the point 2f, which we have observed even with our experiment. So to find the focal length, you have to add these two values, 20 plus 19.4 divided by 4, because it's 2f and I need to find out f from here. So it turns out to be 9.8 and rough focal length was 10.2. That means our observation was quite close to the result.